Hello dear student, welcome to Department of Chemistry. Myself Patil Jayashree. Today we see the remaining part of spectrophotometry. In the last lecture we studied the single beam photoelectric colorimeter, single beam spectrophotometer, double beam spectrophotometer, spectrophotometric titration, its instrumentation, technique used in spectrophotometric titration, titration curves, advantages of photometric titration, and now we study the application of spectrophotometry. Application of spectrophotometry consists of qualitative analysis, then spectrophotometric study of coordination compound, determination of instability constant, determination of pK value of an indicator, then structure of organic compound, structure of inorganic compound, and qualitative analysis. These are some application of spectrophotometry. Let us see in detail the application of spectrophotometry. In that, first one is quantitative analysis. Generally, the colorimetric and spectrophotometric quantitative analysis is basically due to the Bayes' law. In short, the analysis is based upon the absorption of light radiation by the absorbing material. Here, the intensity of the light is play an important role. Means how much stronger the color of the solution, that much amount of light get absorbed by that particular solution. The amount of light radiation absorbed is directly proportional to the concentration of the absorbing species in the solution. So for this, it can be seen by three different methods. First one is unknown concentration method. This method is done by constructing a calibration curve as per the Bayes' law. In this particular case, we are prepare a series of solution, and from that we are select a blank solution. That blank solution is used for the selection of lambda max, also for the adjusting the 100% transmittance and 0 absorbance. After adjustment of the instrument, we can measure one by the same cuvette size the absorbance of the particular solution. After getting the series of solution absorbance, we place a plot of graph absorbance versus concentration, and from that calibration curve we can easily find out the unknown concentration of the solution, also the its absorbance. Okay, then the solution of the unknown concentration is treated in the identical way, and its absorbance is determined using the same cuvette and wavelength that I already telling you. Knowing the absorbance of the unknown, its concentration is determined with the help of the calibration curve. This is all about the qualitative analysis first, quantitative analysis first method. Then in the second method, unknown concentration by the method second, we can find out. In that particular case, we are applying the Bayes' law. For that purpose, we are considering the two equation. A1 is equal to A1 B1 C1 and A2 is equal to A2 B2 C2, and this is nothing but the Bayes' law for the known concentration always as for the unknown concentration. Absorbing species both are the same, and therefore absorbance A1 is equal to A2 and B1 is equal to B2, and for that purpose we are having the new ratio, that is concentration C1 divided by concentration C2 is equal to A1 divided by A2. By knowing the 3 quantity out of 4, we can easily find out the single quantity of the unknown concentration. So all about the method. In method third, we can easily find out the unknown concentration can be easily determined with the help of spectrophotometer and Bayes' law. According to this, we can use A is equal to log P0 divided by P, or this can be right log 1 by T, that is nothing but the ratio of transmittance, or it is equal to AB C, that is nothing but the Bayes' law. In spectrophotometry, the path length B is constant for a given pair of matched cuvettes, and then radiant power of incident light is kept constant under this condition for the given system, and setup of the instrument is carried out. Now C is equal to log P0 divided by P divided by AB. This equation is useful for determining the unknown concentration of the solution. So student, this is all about the quantitative analysis. Generally, to find out the unknown concentration of the solution from the series of solution, we can use the three method: method 1, method 2 and method 3. In method 1, we can use the calibration curve. In method 2, we use Bayes law, and in method 3, we use the spectrophotometer and Bayes law along with the absorbers. Okay, let us see the second application of the spectrophotometer, in which that is nothing but the spectrophotometric study of coordination compound. In that, there are generally three methods are useful. Let us see the first method, that is nothing but the mole ratio method, which is invented by the Yoe and Jones. So, in this particular method, a series of solutions are prepared in which concentration of either metal ion or ligand is kept constant. Out of metal or ligand, we have to make the concentration of one entity constant. The concentration of other component is get varied. The absorbance of this series of solutions are measured at appropriate wavelength. A plot of absorbance as a function of ratio of mole of ligand to a mole of metal ion is obtained. Okay, here we are using a example of diphenyl carbazone per mole of Hg2 plus ion at a wavelength of 520 nanometer and its absorbance. Now the plot is expected to give a straight line from a origin to the point where equivalence amount of the constituent are present. Okay, the curve will then become nearly parallel to the mole ratio axis after equivalent amount of both the one constituent is become excess and remains unconsumed. The increase in concentration of this constituent show no effect on absorbance at a given wavelength. See, in this particular diagram graph, we can easily see that at start the concentration of the ion is get increases and absorbance is also increases. It is a directly proportional relationship, but once the constituent present remains unconsumed, then the graph show a parallel nature with the ratio of y divided by x. Okay, the plot obtained in such a determination is given here, and taking here we are using an example of diphenyl carbazone complex. The metal ion is Hg2 plus ion, that is mercury, and the reagent is diphenyl carbazone. Here the ratio of y divided by x is obtained on a mole ratio. So student, this is one of the most important technique which is asked in number of time in the examination. Let us begin with the next method for the determination of study of coordination compound. That method is Job's continuous various method. Okay, in this particular method, the total molar concentration of the metal ion and ligand is kept constant, but the ratio of the moles of the component is varied in series of the solution. Okay, the total concentration is equal to Cm plus Cl, that is concentration of metal plus concentration of ligand is equal to constant. The absorbance of each solution is plotted as a function of mole fraction of one of the component. The absorbance are measured at the wavelength where the complex shows the maximum absorption. The curve starts from the zero absorbance, and only when only component 1 is present in the solution, the absorbance rises as the second component is added. The absorbance complex is formed. Maximum absorbance is attained when the component 1 is totally chemically reacted with the equivalent amount of the other to form the complex, and not the either of the two left unconsumed. After the maxima is obtained, the absorbance drop down as the concentration of the component are decreases. This point is explained in this particular diagram. Here also we are taking the example of mercury diphenyl carbazone complex. So student, in this particular case we are using at start the absorbance get increases, but when the FM point is get reached, there is maximum equivalent amount of the complex is get generated and no two component species is unconsumed at this stage, and therefore after that addition the continuous method shows the decrease in the absorbance in the solution. Okay, this is all about the continuous variation method. That variation method we can easily find out by the ratio of Fm is equal to x divided by y, and here we are using a x and y concentration of the metal and ligand in that particular coordination complex. Okay, now the third method is nothing but the slope ratio method. This method is restricted to those cases where only one single complex is formed at a time. If the complex formation proceed according to this particular case, the presence of larger excess concentration of y L, if the absorbance due to other species besides is get ignored here. Okay, this is all about the slope ratio method, but out of these three methods, first two methods are very important from the exam point of view. Let us see the third application, that is nothing but the determination of instability constant. The mole ratio method has been used to determine the instability constant of the complexes. If the complex represented by the mRn, where m is the metal ion and r is the reagent, then reaction may be written as m plus nr is equal to mRn. Then we get the concentration of the particular species, and from this we can easily find out the degree of dissociation of the particular complex. Okay, let us begin with the fourth application, that is nothing but the determination of pK value of an indicator. The pK and hence the dissociation constant of an acid-base indicator can be determined spectrophotometrically. Here the acid-base indicator like methyl red to illustrate method of acidic HMR and basic MR minus form the methyl red are considered here. Okay, then determination of pK involves some steps. Both the reactant and product exhibit the strong absorbance peak in the visible portion of the spectrum. So from this we can easily find out the concentration of that species into the solution and their pK value. So spectrophotometry is a very important technique that is useful for the determination of pK value. In the next point, we study the structure of organic compound. Structure of organic, the spectrophotometric measurement is a very useful tool in the elucidation of the structural problem of the organic molecule. Here we are using the particular molecular formula, and from this molecular formula their arrangement and bonding is explained with the help of spectrophotometry. Okay, so spectrophotometry is play a vital role in the determination of the structure elucidation of organic compound. Same thing, the spectrophotometry is useful for the determination of inorganic compound. In this particular case, they are useful for distinguish between the cis and trans isomer of the complex. It helps to study the equilibrium between the octahedral, tetrahedral and square planar, also the 5 coordinated configuration. Okay, cis and trans configuration is easily find out with their graph of absorbance versus wavelength. You know very well that if there is more absorbance, then it shows the higher wavelength, and if there is less absorbance, it shows the less wavelength. Okay, this is all about the structure determination of inorganic complexes. Generally, axial substituents split the octahedral level of the complex twice as much in the trans, and in this case cis orientation where the field is more averaged. Okay, so this particular technique is very useful in the inorganic structure elucidation of the different type of complexes. Next advantage of the or application of the spectrophotometry is qualitative analysis. There are generally 3 main methods is useful here: position and intensity of the absorption band and chromophores. Next is shifting position of the change in intensity of the absorption band and auxochrome, and third one is the modification of absorption band due to change in structure of the solvent. So this is all about the last one application, that is qualitative analysis. This application is this application is very important from the exam point of view. In exam, you can the question asked is what is bathochromic shift, hypochromic shift, hyperchromic shift, hypochromic shift. You have to write. Let us begin with the qualitative analysis. In that, we see the first point, that is nothing but the position and intensity of absorption band and chromophore. Generally, the term chromophore is defined as any group in a molecule which exhibits absorption of electromagnetic radiation in the visible as well as ultraviolet region. Generally, there are two types of chromophores. Chromophore in which the first one is chromophore in which the group is having the pi electrons, and during absorption of radiation they undergo pi to pi star transition. For example, carbon-carbon double bond, carbon-carbon triple bond, then carbon-oxygen double bond, etc. Next is the chromophore in which the group is having pi electron and n bonding electrons, and during absorption of radiation they undergo pi to pi star transition as well as n to pi star transition, and shows the corresponding absorption band in a spectrum. For example, in this particular case we are considering the nitro compounds and azo compounds. So chromophore is nothing but a species which is having a double bond or transition between the pi to pi star and n to pi star. Next is shift in position and change in intensity of charge in intensity of absorption band and oxochrome. Here we are focused on oxochrome. Oxochrome is a group which itself does not act as a chromophore, but when attached to chromophore it shifts the absorption towards the maximum lambda max, towards the longer wavelength, along with an increase in the intensity of absorption. For example, the group which is having electron pair, that is OH, NH2, OR, NHR, NR2, or the group which is capable to donate the electron pair, such a group can act as an oxochrome. Such a oxochrome group, when attached to the chromophore, it brings change in position and intensity of the wavelength. For example, when benzene shows the absorption maximum at 255 nanometer with band intensity 203, but when oxochrome like NH2 group get attached to the benzene ring, it exhibits the absorption maximum at the 280. Means here the intensity change, here the lambda max changes from 255 to 280 nanometer, and band intensity it changes from 202 to 1430. Okay, so the role of oxochrome is what? To increase the intensity of the chromophore. Okay, next is modification of the absorption band due to change in structure of solvent. The position of the absorption maximum and intensity of the absorption bond may be changed due to change in structure of the test molecule or the change in solvent. These changes are generally considered some point. First one is the bathochromic shift. Bathochromic shift. It involves the shift of absorption maximum towards a longer wavelength because the presence of the oxochrome or by change of the solvent. Means it shifts the absorption maximum towards a longer wavelength. The shift of the absorption maximum due to change in solvent is called as the solvent shift. Here is also in this particular graph we consider that in position X, this is a normal wavelength, but when it get attached to the oxochrome, then it shifts its position to Y. Therefore, it increases the wavelength of that particular compound. For example, decrease in polarity of the solvent cause a red shift, that is nothing but the bathochromic shift in the N to pi star transition absorption of the carbonyl compound. Bathochromic shift is also exhibited when two or more chromophore are present in a conjugation in a molecule. Such a type of observed shift helps us to understand the configuration of a molecule which is under study. Here, in general, we focused on shift in maximum wavelength. Next is hypsochromic shift. Hypsochromic shift is also called as a blue shift. it involves the shift of the absorption maximum towards the shorter wavelength. In bathochromic shift, we shift the maximum absorption towards the longer wavelength. Here, in this case, we are shift the absorption maximum towards the shorter wavelength because of the removal of conjugation in a system or by a change of solver. It is completely opposite to that of bathochromic shift or red shift. For example, if aniline shows the absorption maximum at 280 nanometer in acidic medium, it shifts at towards the 200 nanometer. So in this particular case, what happened, the aniline at start having a lone pair along with it, and that lone pair give a conjugation to the pi system of the benzene ring and which have the wavelength near about 280. But when the same molecule, that is aniline, is treated with the acidic medium, the NH2 group get converted into NH3 and it carry a positive charge on it. It does not give the electron pair to the benzene ring, or it having the absence of the electron pair, and therefore it shows the hypsochromic shift into that particular molecule. So in this particular diagram or graph of absorption versus wavelength, the x is the normal one and y is the expected, that is nothing but the hypsochromic shift or blue shift. In this particular case, we see that the absorption at start is maximum, but after some time it get occurred at a shorter wavelength. Next is hyperchromic shift. This effect shows an increase in intensity of absorption, and it usually brought about by the introduction of an oxochrome in a molecule. Here the intensity of a peak get increases by the attachment of the oxochrome, which is explained in this particular graph, that is nothing but the absorption versus wavelength. X is the normal one and y is the expected, that is nothing but the hyperchromic shift. Here the intensity of the graph is increased. For example, pyridine shows the absorption intensity is near about 2750 and that of 2-methylpyridine is 3560. The observed increase in intensity from 2750 to 3560 is due to introduction of the methyl group at the position 2 of the pyridine. Okay, this is the hyperchromic shift. Here the intensity of the absorption is get increased. Next is hypochromic shift. The hypochromic shift is completely opposite to that of the hyperchromic shift. In this particular case, we consider the effect shows the decrease in intensity of the absorption. It is usually brought about by the introduction of the certain group in a molecule which is under study. This group distorts the geometry of the molecule. For example, methyl group is introduced in the position 2 of the biphenyl group, then distortion of a biphenyl group occurs and there is hypochromic shift is observed. See in this particular graph of absorption versus wavelength, x is the normal peak and y is nothing but the hypochromic shift which is occurred by the introduction of the methyl group at a position second of a biphenyl group. So student, from the exam point of view, this 4 definition is very important for 1 or 2 marks. Thank you.